Recently on Makers Muse, I put up a video of this, my combat robot inspired fidget spinner maker coin, and a lot of people asked how I made it. So this was designed in Fusion 360, as you would have seen with the time lapse in that video. But let's be honest, there was a lot of movie magic in that video. I didn't show the iterative process behind getting to this point because I did not just draw this and print it and get it right first shot. I had to take a few attempts at it. So in this video, I thought I'd go through my actual design process and what I changed and things I learnt while designing this fidget spinner. Let's get started. Welcome back to Makers Muse, guys. So it all started a few weeks ago with this. I did a Fusion video for my CAD for Newbies tutorial on making a maker coin. Really basic, something that anyone could pick up who have never used 3D modeling before. They could draw in Fusion 360 their very own 3D printable maker coin. But I did these little teeth on it and I thought immediately, okay, these fidget spinner things are taking off. I like the idea of one that has teeth on it. So I drew this sort of with that in the back of my mind. Then as the weeks went on, I thought, okay, I got to make a fidget spinner using this technique. So my design process was this. I wanted to design a very small fidget spinner with teeth on it. And this was the first version. So the CAD file I drew in Fusion is still based off this original, but a lot of things changed, which I'll go through in a minute. And the idea behind this one is I thought to get a longer spin time, I'd use a smaller bearing, which would then have less friction. So this has very tiny bearings, actually. These are from a model helicopter. I bought loads of Hobby King ages ago. Loads of bearings, not model helicopters. And the idea would be that these caps sit on it, like this, with the M3 screw, and it would work like that. But immediately there was a fairly big flaw. Although the thing does spin, as you can see there, it doesn't spin for very long because there's not much inertia in the plastic itself. And as soon as you tighten the caps up, no chance. You can hear that noise there. Even if I try to line them up perfectly, they still rub. And that's terrible for getting a long spin time off your fidget spinner. And there's a few reasons why. Mostly it comes down to tolerance. So tolerance is something that I'll be talking about a lot in this channel in future as I go into more and more future in detail advanced 3D modeling tutorials. But the basic idea behind tolerance is nothing is exact. There's no such thing as an exact measurement. You can design something to be exactly 1 centimeter long. You're never going to print it exactly 1 centimeter long. You'll print it to be 1 centimeter long plus or minus a certain amount. And that's your tolerance or your allowance for parts to be a different size. So 3D printing, especially FDM, you've got a 0.4 millimeter nozzle in most cases. Printing something that small, yeah, not really going to be much luck in getting it accurate. And also, you're getting slop from like the screw itself isn't perfectly 3 millimeters, is it? It's an M3, not 3 millimeter shaft. So that wobbles as well. So I went back to the drawing board with that, and I thought, okay, could I use maybe caps instead? With a 3 millimeter push fit stub, which did work kind of, but again, there was just too much flex in the plastic, and the stub, of course, broke off because FDM isn't very strong. So let's dive into the CAD, and I'll show you what my final version looks like and how I got there. So what you see here is the final version combat robot inspired maker coin fidget spinner that I designed in Fusion 360, and I even gave it some color, which looks quite nice. But this was quite, as I said, a complicated thing to design. Really, it's a simple concept, but getting the nuances and the details correct was what took the longest. I spent quite a few hours drawing this file. But at the base of it, it's pretty simple. We've got sort of revolved features to form this outside part and these inner caps. We've got these extrude features to form these teeth. We've got a few revolve cut features to cut those chamfers, those edges onto those teeth. And then we've got a few superficial details like my logo. But let's go scroll back on our feature tree all the way back. Let's go back into time. This is the first thing I drew, and this is practice that I've been doing for quite some time coming from SolidWorks. And I'm not saying it's correct, this is just how I operate. This is my bearing. So this is what everything sits on. Everything relates back to the size of this ball bearing. So although my original version had these tiny helicopter bearings, I quickly realized that these were too small and too finicky to use. And using a skate bearing at the size I wanted to print, quite small, wouldn't be realistic. It would be too bulky and I wouldn't get enough spin times because there'd just be too much friction, too much rolling friction. So I came across these, which I've had for ages. And these little bearings are from VCRs or VHS tape players. And basically those tape players have a drum, which the tape goes around and it sort of maintains the correct speed of the drum. The tape, to play it through the player. And these bearings are designed to last for ages, revolve for years and years at a time, and just keep going. And they even have these really nice hardened steel shafts. When I was growing up, people were throwing away VCRs because DVDs were becoming popular. So I have loads of these really high quality small bearings. And some of them are better than others because I've used them in various projects, but that's just the bearing spinning. And yes, you can get ceramic bearings. Ceramic bearings would be far better, but I wasn't about to go and splurge loads of money on ceramic bearings for a fidget spinner, let's be honest. So this is the bearing template that I started with, and because I designed this file parametrically, everything's got relations back to each other. So when I changed the size of this bearing, which I did to reflect the new size for the VCR bearings, everything updated. I should have made it a component initially, but I did forget that, so then I made it a component, and that's the name of the bearing if you're interested, R1560ZZ. That's the type of bearing you can buy off VXB if you're interested. So then I did a revolve, and this is how I like to model things like this. You can use extrudes, but I tend to work in revolves because they're a more sophisticated way of getting detail into a single feature instead of doing multiple features like you'd have to do with an extrude. And you'll see why when we do our next revolve for the part. But let's just dive in here, right click the sketch, edit sketch. Okay. So what you can see here, this purple detail here, pinky, purple, magenta, whatever you want to call it, that's a projected line from our bearing. So our outside of our fidget spinner here is referenced to that bearing. So when I change the size of my bearing, this part updates. And where you put your dimensions is really critical in terms of how things update. So for example, you can see this 16 millimeter dimension here. That's referencing from the bearing to the outside of the part. But that measurement will be just as valid if I dumped it from the outside of our spinner to our origin, 23.5. It's still just as relevant, but if I change my bearing size now, it's not going to update how I want it to. It's going to either stretch or or shrink this part here instead of actually making it just follow the size of the bearing. So undo that. I don't want that. And I was changing this sketch all the way up to the end. So what I have here are two almost identical versions of the final fidget spinner. This is the final one, and this is the one that didn't quite make the cut. And they look identical. If I pop the caps off, which a little bit difficult to do, there you go. So those are the two. And there's almost nothing different with them, except if you look at them sideways, a slight increase in thickness. And with this one, there is no chamfer on the inside face. And I did that for a reason, because this one, with the chamfer, if I put my caps on, hear that? There's just enough play in that ball bearing in the middle, because I've only got one ball bearing, that when you move the spinner, because of gyroscopic precession, the caps rub. But if I was to put these caps on the final version, this one, without that chamfer on the inner lip, and spin it, there you go. Just a little bit more clearance to make it spin freely, even with gyroscopic precession moving things slightly. So I was changing small details like this quite often. You'll probably notice as well that this doesn't look at all like the final fidget spinner design, and that's because it's just half of my design. And it's good practice, because if you're designing something to be symmetrical in some way or form, you really want to mirror that final body rather than mirroring the sketch, because mirrored sketches, at least in my experience, tend to explode if you make them too complicated. If you make edits to one side, it needs to replicate on the other side. If you end up going and deleting parts and then trying to reform it, the mirror of the sketch you have can't reform those parts you've deleted. It's better to basically make a mirror of a body rather than making a mirror of a sketch. You still can do them, but just words of wisdom, you're better with a body. So that's what I did, but before I got to that, I had to make my little caps. So to do that, made a new component, and I've got a sketch here. And this is the most complicated sketch in the whole part. And it shouldn't be, because it's a cap. Like, why should that be so complicated? Well, I'll show you why. So let's fire up the sketch. Actually, you can't even see it. There we go. Now I can see it. Right click, edit sketch. Okay. Alrighty, feast your eyes on this. So this is the sketch for the cap. And as I said before, small details like the chamfer edge were rubbing. And the takeaway of this video, if you don't remember anything else, remember this. When you're 3D modeling, everything looks massive. Like the gaps here in this part look humongous. But then you look, actually, it's only 1 millimeter and only 0.8 millimeters. And that's 2 millimeters. It's actually tiny. And you think, okay, that gap there between the edge of my cap and the body of the spinner, 1 millimeter, like that, I was doing 0.5 before and it was rubbing. I'm like, why is it rubbing? 1 millimeter looks huge in the CAD, but that's the final design. Like, it's tiny. And because 3D printing is not accurate enough to deal with those sort of tolerances, you have to allow for it. So because this design has this undercover area here, which helps it spin for a while, there's less air resistance, I made these cutouts to allow for as much clearance as possible while still supporting the caps off the bearing. So you need this little area here, which is a lip. Because what you can see here is there's a tiny lip right there. That's required to sit on the inner race of the bearing to let it spin freely. If we didn't have that, it would be rubbing on both faces and the bearing would be pointless. And that has to sit on this little seat there. Without that, again, they would rub. So everything else around it has to clear nicely while still looking aesthetically pleasing. Another small detail you'll notice is this tiny little chamfer here. And the fact, if you can tell in this drawing, it's very hard to see that my inner spoke for the caps is actually bigger than the whole of my bearing. You can see there, it's actually larger. And that's because the tolerances of my Prusa i3 Mark II, if I made them the same size, which normally would be an interference fit, they were too small. So this is very machine specific. Some of you guys might be printing this file and finding that it's too tight. Well, that's why I offered the source files as well to go in and change these things. But all in all, this is tiny detail that no one would ever see, but it's purely there to let the thing function. Okay, so we're getting there. We've got the cap and half the body. So what's the next step? As I said, mirroring. So what I did is I mirrored the other half of the body and I combined them together. So we're starting to get that sort of fidget spinner shape, but there's not really any mass to it, which is what the teeth were meant to do. So I started drawing the teeth next. So I'm going to go into that sketch, edit sketch. Here we go. And the way I drew these teeth is very much similar to the way I did the Maker coins, but with one key difference. I used a type of a reference called a tangential reference. And I didn't use that in the Maker coin because it's quite complicated to explain. But a tangential reference means that this circle here will actually meet up perfectly with a curve of the inner circle, even though they're a different size. And that's different to the Maker coins I did previously because those circles just sort of stopped and there's like an abrupt sort of meeting of the other curve. Tangentially, these actually don't do that. They perfectly meet up and you get a lovely sweeping curve. I must admit, I do love my tangential constraints. If you ever want to do them, you just hold down Shift and select the two circles that you want to add the tangent constraint, right click, and then tangent right there. But I've already got it there. I've already got it, so I'm not going to do it. Alright, and this is where I was tweaking my tooth size. So the tooth size was set fairly early on, but one thing I didn't have set was this, which is a hole for the weights. So initially, as I said, this was my first version, and it's very blatantly obvious that there's not enough inertia to keep this sort of thing spinning. So I looked online to see what people were using as weights. A lot of people use ball... That's right, that's an old version. A lot of people use ball bearings, which did not suit my design at all. They'd be too large and not enough weight. I initially actually was looking for tungsten carbide of some kind because it's very heavy and dense. Alas, if I did find it, it would have been too expensive anyway, but I couldn't find it. Eventually, I found these though. So these are on eBay. These are literally just 8mm steel balls. I was hoping they'd be protected, but they look like they're just straight steel. And the packaging that it came with says high carbon steel balls and general purpose bearing duty for slingshots and shotgun ammunition, even though the website I bought them from, the page on eBay, said not for use as projectiles. Yeah, anyway, so I don't know how long this will last before rusting. Some guys have told me that they're not going to last very long at all. But they do have the nice amount of weight to them, which is what I need to get the thing spinning. So I designed this hole here to be 8mm in diameter, and it just so happened that that works perfectly with these balls without any changes in tolerances. It's a very nice press fit. I used my hammer, as you would have seen in the video, to get it into place, and yeah, they're not coming out. You can move them slightly with your fingers, but normal operation, normal duty, they're not going to come out. So that was a change I did at the end. So I went back to this sketch. This wasn't here originally. And I did it, and you can see there another tangential constraint to lock where I want that hole. It is blue for some reason. I'm not sure why. That is fully constrained. So you notice I only drew one tooth. That's how the tooth looks. So again, it's better to pattern a body or a feature rather than patterning a sketch if you can avoid it. So that's what I did here, and I ended up creating a pattern. But before I did the pattern, because I wanted to make my model look pretty, this is completely unnecessary, but I dropped some 3D model ball bearings in, as you can see here. But to do that, it was a little bit tricky because, as you can see, it's off axis. So I could have drawn a sketch on my top plane, which is there, there in the middle of the sketch, and then done a revolve there. But I wanted to be tricky, so what I did is I created this... I created an axis through that hole, which you can do under the construct menu. You want an axis through a cylinder, whatever. And then I created a plane that goes through that axis and the middle origin axis. So, sorry, that would be the Z, the Z axis, which you can see here. So that is created through the Z plane axis, and the axis I created through that cylinder. And then from there, I created my little ball bearing in that cutout using a projected and intersected line, as I mentioned before. And then I patterned that original extrude around, and then I patterned my ball bearings around after adding a constraint in so they wouldn't explode into space. Completely unnecessary. There's no reason you'd need to do that if you're designing this for 3D printing, but I wanted to have a nice looking model for the video. So the final detail to make this thing look sexy was to do this, which was to give those edges a nice chamfer. And that was very simple to do, actually probably one of the simplest functions in this video. It was basically this sketch here. So this one used to be in the original version, which I dropped. So the original design used to have this angle flowing off down towards the edges of the teeth, which I really wanted to keep. It looked really nice and sexy, but it wasn't possible with making the thing bigger. It would have had to make it a lot thicker as well. So I ended up just breaking that constraint. It used to be, as I said, constrained to like an angle there. That line there was continued on through the cutout. So I just did this, and it's pretty messy. But, there's areas here, like that's just wrong. To stop that happening, right click, horizontal, vertical lock. Oh, that's all I needed to do. So, like details like this, it's a cut. It's a revolve cut, so you don't really care how far it cuts out of the part. You just care where it's cutting. So that's what I did. And then that cut, that revolve cut, which you can see there, cuts those faces down and makes it look nice and sexy. Also means when you put it on a desk, it's going to sit off the desk and spin. like that. Basically from here on, the part's finished. So if I go to my analysis, which is a cross-section analysis, you can see that everything you need to print this is finished. You're not going to print the bearing, you don't care about that. You're going to print your face there, which is your cap, and you're going to print the main part here. The rest from here is cosmetic, and I want to add my logo onto it, like so. And that's done by adding a SVG into the model and using that SVG file, a vector file, to do an extrude cut. So just turn analysis off. So to do that, I stuck in a plane hovering above the part, and again, there's reasons for why I did this, because initially this is how the faces look. They were quite small, and you can see there, kind of, the logo goes and follows the taper of the part. And to do that, you can do it in Fusion by doing a uniform offset of a object, but because by the time I changed the size of things, the logo was only going to occupy this area, it was completely unnecessary. So that's why it's an offset plane. But basically, here's the SVG. Another strange thing about SVG, sometimes you bring them in and lines are missing. So this blue line there, it didn't import. It imported all the green, but not that blue one. So I had to add that in myself. So you drag that in and scale it to suit. And then I basically made that go project down to the object. So it's an extent to object with an offset of 0.5. So that's what I was talking about. If you want to make a extrude cut into a curved object, like an angled face, something like that, you do that using the to object extent, and then you offset it from the selected face by a certain amount. A little bit tricky to do. It's a bit buggy, let's put it that way. But I did get it to work initially, and then I didn't need it. So this is the final design, essentially. And from here, I just did some tiny chamfers to the design. So if I go to edit here, these chamfers were just to allow some clearance again. And then there was basically just a few in place constraints, because I am working with components and they would explode otherwise. So these constraints lock them in place. And then from here, I just basically mirrored the bearing, completely unnecessary. Mirrored the cap, again, unnecessary if you're printing it. This is just for visual looks. And married a few things together. And that's the design. So, as you can see, if you've made it through this video of rambling, design is not perfect first go. It took me about 3 shots, which is usually how long it takes. And I went from this original design, which was too small, everywhere, too small and too fragile to work properly as a spinner, to this one, which was almost correct. And I did spend a lot of time trying to get the caps right on the original one. I mean, look, I've got loads of these caps, trying to get the tolerances right. It was just too small. So I went back to the drawing board, got this one with the weights. It was almost perfect, as you saw, but it still rubbed a bit. So I ended up with this one. And this one is still not perfect. I'm going to be completely honest with you. The caps, as I've been using it, if you put pressure on the edges like that, you need to hold it in the center for it to work, because the cap pegs have worn out since I've been playing with it and dropping it, stuff like that. A little bit of super glue in the middle might fix it, but then I can't ever take it apart. But yeah, thanks for watching, guys. Hope you found this video interesting on how I design things. And the fact is, nothing's ever right first time. You're always going to make mistakes. But the main takeaway of this video is to just pump parts out quickly, to then iterate the design and move on to a better design later on, instead of trying to polish something before testing it. And always remember that when you're 3D modeling things, distances and gaps always look massive in your 3D model, but in real life, they're going to be a lot smaller. So keep that in mind when you're 3D modeling, and you're going to run into a lot less pain, and you're more likely to get something like this to work first go. Anyway, thanks for watching, guys. Hope you enjoyed this video here on Makers Muse. If you want to see future 3D printing tips, tricks, Fusion videos, loads of stuff coming, then hit that subscribe button. Helps me out a huge amount, and look forward to seeing you again very shortly. Catch you later, guys. Bye. It's almost silent. Wow, 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 wow.